Great. All right, I think I'm gonna first, can everyone hear okay? All right, cool. So I'm gonna first just share like a kind of rough outline. So the general idea, we want to give like a overall sense and kind of comfortability with blockchain. So yeah, so I will try to share this here so you get a kind of sense of what we'll try to go over. I don't know if you guys are interested in other things, we can definitely try to pivot towards that. Sharing notes. Cool. So you guys should be able to see the note screen now. Great. Yeah, so kind of lost a bit of formatting here, but first we'll start with kind of why we do blockchain to begin with. So the actual problem that blockchain is trying to solve, which is maybe quite a bit different from what you might have in mind. So we'll start off with kind of the foundations there. Then after that, go into a couple different like high-level approaches to solving that problem. And then once we have the kind of high-level approaches, then we can go down into some specifics on like blockchains you might have heard of, like Bitcoin, Ethereum, and how some other like altcoin blockchains might kind of tie into that. And then finally, can go over some like potentials for like scaling, so that, you know, even these blockchains that might not seem too viable and scalable, like Bitcoin and Ethereum, like you might have heard that they're not like as good as some others. There's actually ways that we can kind of work around that. So I'll go over some kind of an overview of what we can do to bypass those limitations. Cool. So, so starting off, so what blockchain is trying to solve is essentially this distributed consensus problem, which sounds kind of fancy, but basically we have a bunch of machines that might be in different locations, like across the world, and we all want to agree on one thing, and that's as simple as that. So let's say we're trying to agree on like a grocery list, and everyone kind of has a different idea of a grocery list, but then, you know, when everyone kind of puts in their value, their idea of what the grocery list should be, ultimately we come out with one single grocery list, and that's what we want. So that's basically what blockchain is doing. So maybe it's in the form of like transacting like cryptocurrency from one account to another. Maybe it's in the form of doing some more complex computation, but that's all it's really doing. So there's kind of two basic models that you like kind of start out with. And then blockchain itself actually lies in this third model that is kind of in between the first two here. So so in like a really simple world, we can think of this synchronous model. And basically here, like time progresses in steps. So like you can only send a single message when you're trying to like make one of these agreements on what the value should be, like once every hour or something like that. So of course, this is kind of limiting for a few reasons. So for one, we have to kind of guarantee that everyone's going to receive that same message in that hour, but that's not really practical. Just because like maybe their internet's down and they're not going to receive the message, and maybe they don't send a message, and we're kind of stuck just waiting for them. So in that case, there's some issues that can happen, and basically it can work really well if we can guarantee that, but it's very impractical to guarantee that in this blockchain setting. So we can think of, on the other side of the coin, a fully asynchronous model. So this is where we have no guarantee whatsoever that we're ever going to actually receive any messages from any other node in the blockchain. Let's take out the word of blockchain. So just like there are nodes that are participating and trying to agree on some value. So let's take out the idea of blockchain for now, and don't even worry about that yet. So really, everyone is trying to agree on a single value, and there's no shared notion of time. So because there's no shared notion of time, when we receive a message, we don't know actually exactly when the sender sent it. If there were maybe messages in between that we didn't get just due to network delay, or maybe we just don't get it in any like bounded amount of time. So like if we say that, okay, surely we'll get a message within a year, we can't even guarantee that. So no matter what, this is kind of like going to be tough to work with. So maybe a more realistic model is this partially synchronous model, which is really what pretty much all blockchains are based off of now. So in this partially synchronous model, we have some time. We are basically in the asynchronous model, except there are some times where we can have a bit of synchronous communication. So even if we're not always going to be synchronously communicating, we'll at least be able to synchronously communicate for a short amount of time, so we get some kind of progress made. So we can think of these asynchronous times as like when maybe some servers are down, or there's some like attack on the network. And because of that, we can't really make progress. But ultimately, as kind of an assumption of this model, we're always going to get back to the point where we can communicate with everyone, and we'll be able to receive enough or pass enough messages between each other. Great. So that is kind of the very fundamental, like what problem we are trying to solve with blockchain. So going into kind of some options for how we can solve this, there are a few different kind of high level techniques, I guess, that are out there. So first, let me reorganize this a little. And please, if there are any questions, let me know, because I know that this might be a little technical, especially right now. So yeah, any questions, go for it. But I'll just take a second to reorganize here.
Do you have an example of when you don't have the blockchain, what happens? So I guess you were kind of talking about both of those cases.
When you don't have a blockchain?
When you don't have a blockchain for that partially synchronous model.
Well, so not having a blockchain. So really the blockchain is the solution to the problem, okay, if that makes sense. So maybe there could be a different solution to a problem that is not explicitly a blockchain, but the blockchain solution is just what we're going to focus on here. Okay. There are definitely kind of slight alternatives, like a block mesh I've heard of, and things like that. But yeah, I think overall blockchain is the solution that we're going to focus on.
And at this point, we don't have to know what blockchain is yet.
Correct. Yep. Okay, good. Yeah, you don't have to actually worry about what blockchain is yet, and we'll get to that very soon in this kind of next section. Cool. So yeah, I guess before we actually go into the high-level strategies themselves, let's talk about two different desired qualities of anything that solves this partially synchronous model. So the two things here are validity and liveness. So liveness essentially just means that if you are a user of this model, so you have some transactions that it's like, hey, I want everyone to know about this. Liveness guarantees that if you put in a transaction, that people will eventually know about it. And yeah, so if they know about it once you put in the transaction, then that makes it so that we actually have liveness, and we'll see that one of the strategies, like kind of high level strategies that we go for with blockchain, will focus on this as its primary goal. The other option, or the other quality, is validity. So this guarantees that any like two nodes in participating in the network all have a consistent kind of ordering of transactions and nothing that is conflicting. So really, you can think of all the history of transactions that any node participating in the network has is like a list. And this list has an order. So like this is the most recent transaction, this is the second most recent transaction, third, fourth, fifth. And if our solution to this partially synchronous model is valid, then that means that this order is going to be the same for everyone. And so yeah, so if it's the same for everyone, then, well, so okay, so maybe not quite the same for everyone, but the only difference should be that one is a prefix of the other. So basically, maybe we haven't actually received the information yet, but over time we will actually receive the updated information, and we'll all have the same list.
This goes to your point that if one site is down, one node is down at the time that something was sent, they might not have everything that they should have.
Yeah, so like maybe if one node goes down, one site goes down that's trying to run a node, then it might take them a little while to actually get back. Yeah, right, for sure. So they'll be behind, but as they receive those transactions, they will be able to execute them and kind of catch up to the rest of the network. Yeah.
And if they get them in a different order, that's okay too, because they know how to sort it properly.
So they might, so kind of a part of this validity guarantees that when they enter these transactions into their own like idea of what I guess the global state is. So like basically what they think has happened everywhere, like that everyone had, like all the transactions that everyone has entered. Validity makes sure that this is all consistent and this all lines up, and it's never going to be conflicting between two nodes, two different nodes. So basically, if we have this property, then that we won't have to worry about what order we maybe receive the messages themselves, because our protocol is designed to handle that.
Okay.
Yeah. Cool. Yeah, please ask any questions, or if it's just like this is too technical, I need something like higher level. That's a perfectly valid thing right now, because I have been doing this for like a semester now, so I'm coming from a different perspective. So yeah. All right, cool. So let's, now that we actually know these two properties, let's go through the kind of two techniques that we can use to kind of prioritize either one or the other. So the two main techniques are this BFT-type protocol or the longest chain type protocol. And when I say protocol, that's basically just the solution to this partially synchronous model problem. So that's like what every node in the network will be running on their computer. It's the application that they'll start up and say, I'm running Bitcoin now, right? So that is essentially the protocol that I'm talking about here. So these protocols take two different forms, mainly. So it's this BFT type, which is just, you do not need to know this, but it's Byzantine fault tolerance type. Could definitely go into more of that, but that's very technical. And then the longest chain type, which you might have heard something about longest chain before when it comes to Bitcoin or Ethereum, or maybe not, and that's fine. So these are the two main types. Don't worry so much about how they're actually implemented or anything. That doesn't really matter, to just kind of have a high level knowledge of blockchain at all. So don't worry about the details there. The main important thing is that BFT type preserves validity, and longest chain preserves liveness. So this might be like a little surprising that that like longest chain would like preserve liveness and not validity, right? That like it's really focusing on making sure that you can enter your transactions. It doesn't really care about if they're all ordered properly, and that seems a little like, isn't like having them ordered properly really what we care about? So I'll go into in a minute how we can kind of work around this and even have some kind of guarantees even when the transactions aren't ordered properly. But yeah, so so one thing to keep in mind about both of these is that depending on what kind of protocol you choose, you might have a different requirement on how much of your network has to be honestly participating. So like actually running the protocol. Because if not, they might be actually like a malicious attacker that's trying to break your protocol actively, like doing everything they can to like break validity or break liveness. And if our protocol is well designed, we have some amount of tolerance to this, but it's never going to be perfect. We're never going to be able to actually have both validity and liveness when there are like a significant amount of malicious attackers. So this is a pretty commonly known problem, and there are some theorems about it with like having to do with like maybe what you can get with only having a third honest nodes or like 2/3 honest nodes. But ultimately, this really comes down to if you have enough honest nodes, then you're fine. Maybe it's 1/3, maybe it's 2/3, but that's okay. So like just as an example, the BFT type, so long as you have less than 1/3 attackers, then everything runs fine and smoothly. If you have anywhere between 1/3 and 2/3 attackers, you lose liveness. You lose liveness. So you can no longer actually enter any more transactions, but validity is always maintained, so long as you have under 2/3 attackers. So there are some large blockchains that actually opt for this, and so if they choose this, they might have some attacks like a DDoS attack or something, where someone who just really doesn't like this this blockchain, they're trying to shut it down, and they attack it for like a week, and it goes down for a week, and you can't use it the entire time. But once they're done attacking, you can go back to using it. So that's the kind of a bit of a trade-off that we make here. With the longest chain, generally it's going to be 50% that you need to be honest. So if you have any more than 50% attackers, then you can really break down even validity. So that is going to be a bit of an issue. So even if you do still have liveness, if your validity breaks down, that can be pretty bad. So at the same time, let's see. Yeah. Okay. Well, I'll go from there. Yeah. So, all right. So it's pretty clear that with the BFT type protocol, you just kind of go off of what everyone kind of agrees is the current state. That is the current like list of transactions. So there's not too much to worry about there. Sometimes maybe you won't be getting any new transactions, but eventually you'll get back to getting some more transactions. With the longest chain, the thing is about the longest chain is that whenever you kind of enter some new transactions, maybe you don't agree with your neighbor on what the transaction just before the transaction that you entered was. So maybe like going back to like the grocery list example, maybe you wanted to add milk to the grocery list. Gareth wanted to add orange juice to the grocery list, and then like both of you added it at the same time, but there's like only space for one of those on the list. And then whose gets added? Maybe we each like kind of think that our own is getting added, and that might be okay. That's the thing about longest chain, is that you don't need to all agree on the same ordering of transactions. At least at the point where you actually are entering those transactions. So so I'll basically have my own copy of the grocery list. Gareth will have his own copy of the grocery list, and at that point we'll kind of diverge almost. And what do we do in that case? So once we have these kind of two grocery lists in parallel, we're going to have to do something to really understand which we want to keep going with. So maybe some other people keep on adding on to Gareth's grocery list. So that gets like longer and longer and longer, and no one really adds on to mine. They weren't like, maybe they like didn't get the message about me adding the milk to the grocery list, and they went on with Gareth's. So so he ends up with a really long list, and these are all the groceries that I want to add, and I kind of like stagnate there, and maybe I add one or two more things, but you know, Gareth ends up with a longer list. So this one
wins, the longer one wins.
Yeah. So so as part of the protocol, we actually decide to pick this longer list or this longer chain as the one that we should add on to. So if we are aware of this of a longest chain, and that is exactly where this comes from, then we should be adding on our transactions to that list. So it's possible that that just because of like network delay or something, we don't actually know what the true longest chain is. Like maybe there were some other people who were like each adding to their own lists, and we each like added one item, and maybe there's some ties even, or maybe we just don't know about it because the network is really slow that day. And that's okay. So we can still add blocks kind of in parallel, but so long as but so long as we like eventually receive some information about a longer chain, we're going to have to switch our mind that this is what we have to put all of our transactions on, and don't care about the rest of it. So in this sense, there are kind of multiple copies of what the world should be, but we only really listen to the one that like most people have added on to, that has the most items, the most transactions on it. So
what could you, in real world, when could you get away with that and when could you not? Like, let's say banking transactions, which you really have to prefer the validity over the longest chain, right?
Yeah, so in things like banking transactions, things where you really want to like make sure something is really secure, you definitely want the BFT type. The BFT type, which is the validity based. Yeah. So one way to kind of get around this in the longest chain setting is just to wait until the longest chain is a lot longer than any other chain. So this is like, it sounds like kind of silly and kind of iffy, but this is exactly what you do in things like Bitcoin, Ethereum. A lot of these main longest chain based protocols, you actually do this. So like for Bitcoin, you a kind of typical waiting time is about like 6 blocks. So I'll introduce the concept of a block here. So basically we've been talking about individual transactions, like individual items on a grocery list so far. But more generally, these can actually be, these are really blocks of transactions. So you can think of this like a whole bunch of items that I've written on a grocery list that I want to say, like add to the total list.
So you just pick a random number like 10 or something like that?
Yeah, so depending on what kind of like your exact design of your blockchain and everything, maybe you can fit different amounts of transactions on it. And maybe those transactions actually have some computation in them, like built into them, that that have to be run by everyone that's like that's looking at that transaction. So I can get into that a little bit more later, but yeah, basically you have to yeah, so sorry, so back to your
just a random size, you know, we pick it based on what's practical in your world.
Yeah, whatever's practical. Some considerations there are like if it's like too big, then maybe you're going to end up with a bunch of transactions that don't end up on the longest chain, and that's going to be pretty annoying for some people. If it's too small, then you might let's see. Okay, sorry, no. So if it's too big, you might end up adding it too slowly, adding these too slowly, and you won't be able to add like sequential transactions as quickly as you would like. If it's too small, then you might end up with a lot of transactions that aren't on the longest chain, because they will end up kind of in parallel. And we call that a fork when that happens. So when two people add transactions that kind of diverge, like Gareth adding the orange juice while I'm adding the milk, that actually creates a fork in the blockchain, where one will probably eventually become the longest chain, but as of now it's kind of forked, and it's maybe unclear as to which is actually going to become the longest. Yeah.
Is there anything in the world that allows people to merge a forked chain to?
There are some techniques about this. So like Ethereum specifically has some things built into the reward system, where like if you include one of these so-called orphaned blocks, then you can actually like get a bit of extra reward for yourself, and they actually get a bit of extra reward, since like, oh, you know, you mined this block, but you didn't quite, it didn't end up on the longest chain, but we'll still give you some, even though, like, because clearly you were pretty close, and you were seemingly being honest about it.
But still, it's discarded in the end anyway. They might reward the miner, and that's a new concept too. None of us.
Yeah. So miner is a new concept. Yeah, and we can go into more of that too. But if you want to look that up or anything, it's called like uncle rewards and nephew rewards. So basically, like you have an uncle of your longest chain, and you want to include the transactions that your uncle said should be on there. So cool. Yeah. Okay. Does anyone else have like questions about that? There's a lot there. Okay.
I'll wait to the end.
Okay, sure. Cool. Yeah, so we got some more about the longest chain there and everything. Okay, so yeah, so I'll just say, like, a lot of the biggest blockchains right now are actually longest chain. They do prefer this liveness over validity, and a big part about that, I think, is just because you can kind of work around the validity issue by waiting. So by like waiting for 6 blocks, 10 blocks, 1,000 blocks, you can have some kind of like probabilistic guarantee that your transactions, like, that are maybe 10,000 blocks down the longest chain, are going to stay on the longest chain. There's not going to be another chain that ends up passing it. So yeah. Yep. Cool. So, so now, up until this point, we've kind of been talking about a world in which we trust everyone who is participating in this network. But in reality, you know, maybe like one node isn't really just one person. Maybe a single person has spun up like 10,000 nodes, and they shouldn't be able to overtake the network just because they have 10,000 nodes running at the same time. Plus, that's going to really like potentially slow things down. So we don't necessarily want that. So this kind of motivates why we need Sybil resistance, or like proof of X. So whether this is proof of work, proof of stake, proof of space, whatever you want to use. This is why there is a need for this. So I'll start off. Yeah. So that basically is. Yeah. So if we were allowed to just spin up as many nodes as we wanted, and you can think of this as, or these are really called these Sybils. So these like extra kind of versions of yourself, basically, is kind of where it comes from. So you have maybe like many different versions of some evil, malicious participant in the network. But you don't want that evil participant to get all the power just because they have all the nodes. So we need some kind of scarce resource in order to kind of force, or I guess disincentivize spinning up extra nodes like this. So basically, we should have it, there be no real benefit to spinning up extra nodes, because we would still have to use the same or more amount of this scarce resource. So the classic way to do this is this proof of work. So let me reorganize here a little. Alrighty. Good.
POX used to be outdented a bit. POW and POS. POX was outdented from the original. Oh, POX.
That's fine. Okay.
See, right, because we had it originally.
Yeah, I guess I know. I remember now.
Even others was not aligned with POS and POW.
All right. Sorry. All right, great. Cool. So yeah, proof of X. So starting with proof of work. Basically, proof of work is, let's see. Okay. So let's do a little introduction to like an idea in kind of cryptography. So so sounds fancy and everything, but don't worry. So basically, using some kind of cryptographic function, cryptographic hash function, we can take some arbitrary input. So we can say maybe this is a transaction, maybe this is a block, maybe this is just like my name. Maybe that's all it is. It doesn't really matter. So we can take whatever, feed it through this function, and then whatever the output is, we're going to say that this essentially has no way of being reverse engineered. So we can't take this output and then use that to get the inputs back. And this output is basically just a random number. So like a potentially very, very large random number. So there is no real possible way that you could like just iterate through all of the random numbers and figure out what corresponds to it or anything. And that is kind of the assumption that we're making here, that we can't like use a backdoor to get back to our inputs given the output of this pseudo random number generator. So yeah, that's not really what it is, but anyway, yeah, cool. So so that is what roughly what a cryptographic hash function is. So this is what's going to allow us to really do this proof of work. So
is that like where you do the SHA-256?
Exactly, the SHA-256 is
so
an example.
64 character string can never be reversed back to the original.
Exactly.
Form.
Yep.
Okay.
Yep. Yeah. So in this proof of work, what we are trying to do is hash the block that we are trying to add to the longest chain. We're trying to find a hash of that along with like some little random number added so that we can try a bunch of different ones. We're trying to get a hash that outputs a random number that is close to 0. Now this number is, essentially never going to actually be 0 because the odds of that are just so astronomically small, and we're just basically doing a random number, and this is actually like the odds of this are like 1 in 2 to the 256. So an absolutely tiny number that's probably never going to happen. So in order to make this a little more realistic, we add something called a difficulty or a difficulty threshold. So maybe the difficulty threshold is like 2 to the 64. And that means that so long as whatever output we get is less than this number, then we're okay. And that means that this block, we've put in enough effort that this block can be added to the longest chain. This difficulty itself can be kind of adjusted via the protocol itself, and maybe the goal is to add so many blocks in so much amount of time, and as computing power grows, that difficulty is going to kind of adjust with it. But essentially all that we're trying to do is find this number that is low after hashing our block with along with an extra random number. So we're just trying to find a really low output there. And that is what the miners do, or a node, when you are trying to add a block to the longest chain. So so what miners are doing is they're taking a block where they have received transactions from a bunch of different people. They add on a little random number at the end, and this is called a nonce. If that, yeah, it's just called a nonce, like a number used once, but don't worry about that. So we have the block and the nonce, and we put those together, hash it, get the random output, see if it's low. If it's not, we do it again. And we keep on doing this again and again and again and again and again. And maybe we have even dedicated hardware that's really good at this. And you might have heard of ASICs, and that's basically what these are designed to do. Just keep on running these random hash functions over and over and over again in a very parallelized way. So
are you talking about mining at this point?
Yes, yes. And this process of kind of checking different numbers and seeing if they work, that is exactly what mining is. Yeah. So that's what these giant mining companies are doing. They just have a bunch of these, a bunch of these machines with specialized hardware that are just trying out a bunch of different numbers and hoping that they get one that's low. Yeah, so that's basically how we actually make sure that any given node in the network is actually putting in effort, and that no one node can just, or no one person can just spin up a bunch of nodes and overtake everything. All right, so clearly this has some pretty terrible environmental impacts, and also ends up using up a ton of hardware that is really could be used for other more useful things. So it's maybe not the best solution. So all this energy is being wasted into computing all of these numbers that are basically not serving any other purpose other than to decide who's going to add the next block. So it's a lot of work for not a whole lot of result. So as a possibly better alternative, there is something known as proof of stake. And in this case, in proof of stake, we do lose some things depending on exactly how it's designed. There's not like exactly one way to design it perfectly, but the general idea is that rather than using computation as the scarce resource, we use the cryptocurrency linked to the blockchain itself. So I haven't even talked about a cryptocurrency yet. So so basically what a cryptocurrency is a reward that's given out for miners of a block. So like the miners themselves, they're not the ones necessarily that want to add on transactions. They just receive transactions from a bunch of other people, put them together, package them up in a block, put a little bow on it, and then once they have actually mined it and mined that block and gotten that low number, then it can be added on to the longest chain. In the proof of stake setting, rather than just like mining away with your hardware, you just have to have some of the cryptocurrency that is linked to the blockchain itself. So by staking that cryptocurrency over time, so let's say I stake this cryptocurrency for for the upcoming block, and then that's basically I will get a chance proportional to how much I staked. So with a chance proportional to how much I staked, I will get to add the next block. And that is like, yeah, basically. So
is that much more energy efficient then? And
yeah, much more energy efficient because we're not running a bunch of calculations or anything. We're just like at different intervals, we're kind of checking, okay, who has how much staked. And because you can only stake so much because it has real monetary value, that's going to dissuade any kind of people from spinning up a bunch of nodes.
Is this why a crypto.com can make a claim that they're going to be carbon negative within about a year or something like that?
I have no idea how they could be carbon negative.
How they could do that.
Yeah.
Okay.
But that's definitely a big part of it, probably, that that they are proof of stake based, I think. Yeah. Okay. So this is great in terms of environmental impacts because we no longer have to worry about the actual mining. Maybe we have to do a little bit of computation, but nowhere near the proof of work. Yeah. Oh, and I think I actually missed this before, but basically when a miner mines a block, they actually get a reward in the cryptocurrency that is linked to the blockchain. So let's say you're mining a block of Bitcoin, you mined it, and then when you mine it, you are then given what is you're given a bit of Bitcoin that is given to you via a Genesis block. No, sorry, not a Genesis block. The Coinbase transaction, that's what it is. So basically a transaction from like basically no one to you. And and this is like given to you via the protocol. So like that's kind of what guarantees that you get it, just the protocol itself. You don't have to have any kind of centralized source that's saying like, all right, you mine that, you get this. It's just all kind of built in. So so yeah, via these Coinbase transactions, you can make money that way. There are also some like crypto or blockchains that would include like extra, where like extra rewards via users that are submitting transactions, also submitting a transaction fee along with it. And like if you submit a higher fee, maybe the miner gets a little extra reward, so they're more incentivized to actually include that in the block than some other transactions. There's definitely some more we can talk about transaction fees if you guys want, but I think not quite as important probably. But yeah, we can definitely talk about that too. Yeah. So there are alternatives to proof of work and proof of stake, like proof of space or like space time, where like you kind of hold a, you basically like hold some amount of data for a certain amount of time. And according, kind of proportional to that, you have some, I guess, probability of adding the next block. Again, it all kind of comes down to that. So proportional to whatever you are, whatever resource you might get to add a block. Yeah. So that is about it for kind of the basics of blockchain. And then moving on from there, we can talk about kind of scaling blockchain and what we can actually do with blockchain now that it's kind of set up. So for like scaling Bitcoin, there's this Lightning Network. I guess, yeah, even before that, we can talk about scripting. So like there are different kinds of like scripting languages, depending on which blockchain you're on. And maybe they have different capabilities. So like Bitcoin's is very simple because it's really only designed to process like payments, really. So it's pretty limited in what it can do, but it can effectively, transfer payments, not necessarily quickly, but it is good enough that we can actually write some things on top of it that let us do slightly faster transactions, at least with a somewhat known network. Yeah, I think just a quick note on that as a whole, the Lightning Network, like it basically lets us get to a point where maybe some big companies that have regular transactions with each other can make their transactions via Bitcoin a little more efficient, but it's probably not so effective that we can use it for, say, paying for your coffee, right? That's probably not so realistic with Bitcoin specifically, even via the Lightning Network. So there are ways to kind of use an external source to get around this, but not natively through the Bitcoin blockchain itself. So yeah, I think just as a word overall about Bitcoin, I think really its value is in being a store of value, more so than a method of transaction or a method of computation. Yep. So Ethereum, on the other hand, has a much more complex scripting language that is actually can essentially do any kind of computation. And because it can do any kind of computation, you can get much more complex scaling capability off of it. And on top of just scaling capability, you can also use it for much more practical things. So you can have kind of contracts between different people maybe you can form an organization that is dedicated to a certain thing, like a certain purpose, kind of. You can.
Is this where you hear like real estate could use it or something like that?
I'm not sure about real estate.
Okay.
Yeah, where this I was talking about like DAOs, if you heard about like DAOs. Yeah.
What is a DAO?
Decentralized autonomous organization.
Oh, okay.
So basically you can like set up what are known as smart contracts, which is a fancy way to just say some code. So basically like these smart contracts, they let you do pretty much whatever you want. So the only thing is that you have to kind of keep in mind is that whenever the smart contracts are run, you have to actually pay something. Whenever any kind of code is run on something like Ethereum, you have to pay for how much computation you're doing and like how expensive it is. So like maybe storage is especially expensive because every node running Ethereum has to store that data. So that ends up being a lot of storage across everywhere. So
however big the messages or blocks, what the data is contained, every node has to have the entire, is that the ledger?
Yeah, so not okay. Yeah, don't even think about ledger. So okay, I'll just do a kind of side note here. People will talk about ledger and think of that as the grocery list, right? It's a very like, I think it's a very simplified way of thinking about it, where all the transactions that actually matter are payments. But that's not true. That's like a very limited and kind of maybe like in Bitcoin, that's almost true. But like it's I think of it as a list of transactions or a blockchain more than a ledger. I think it's a pretty. So
ledger's like a loaded word because people think automatically of
it's like finance, and that's all you can use it for.
But it exactly. It's that decentralized but repeated body of information that everybody has to agree on. That's the same thing.
Yeah.
Okay.
And kind of the list of like blocks of transactions that you end up with, that is the ledger.
Okay.
Yeah. But anyway, I wouldn't use ledger. So yeah.
So blockchain people in the know don't use ledger.
Oh, some do, but you know.
But
it's that was definitely one that my professor was like, yeah, don't use ledger.
Because Bitcoin led it, and that's
and people like only think of it for the cryptocurrency side of it, not for the actual blockchain. Okay. Yeah.
What are some practical uses of blockchain outside of cryptocurrencies? Just so
some practical uses are like future uses, especially like maybe like a decentralized AWS or something, where you can kind of share computation or storage or whatever you want without having to worry about like any kind of centralized source that has to manage it. And just by running it kind of through the blockchain, you can guarantee
something will get performed,
things like privacy or like that it will get performed. And so like that could be something good. I think I mean, in general, anytime where you have a bunch of people spread like maybe across the world or that don't necessarily trust each other, and you all want to agree on something. So that's kind of a very abstract way of thinking about it. It can be hard to come up with some real applications based off of that. But yeah, I mean, I think especially like the decentralized cloud computing is probably a big one. Yeah. Okay. And that's definitely already being done with things like, I think, Filecoin, like where you can like store data decentralized, things like that. PyPiper. Yeah. Let's see. Cool. So okay. Let's see. Okay. So so Lightning Network we already went over. So then I guess one last thing about like kind of scaling is our rollups. So what rollups are are basically a way of using an extra network in order to help our normal network. So we have one network that is like running Bitcoin, let's say, or let's say Ethereum, because that's more realistic. So we have one network that is running Ethereum. So this is like the Ethereum network. And then on top of that, we kind of have another network that is maybe much smaller, but everyone participating in it has some supercomputers. And they can like calculate things really fast. So what's really the benefit of this? Essentially, what we can do with this is have some much faster transactions, all actually performed on this level 2 network is what it's often called. And then and because we're using these supercomputers, it can be calculated like really quickly, even though we have to kind of trust just a couple supercomputers to kind of do everything, or maybe just even a single computer. So there is an element of trust there where you kind of have to make sure that you actually trust them to be doing what they say they're doing. But if you can do that, if you can like accept that trust, then you can end up getting like a lot more done on something like Ethereum. So something like hundreds of transactions or even thousands of transactions per second, rather than just like tens of transactions per second total. So that's kind of one final pretty big push, I guess. So yeah.
To put it in perspective, like I'm going back to financial transactions, but how many transactions, let's say, how many Visa transactions are there?
So like Visa, I think it's like tens of thousands per second, if not like hundreds of thousands, I think.
And what is the possibility with some cryptocurrency then?
Yeah, so right now it's like using something like Ethereum, capped at about probably 1,000 or so per second.
So it's actually like less than
definitely less right now. There are some cryptocurrencies that natively try to optimize that though, and can actually get quite a bit more. Yeah.
But a complaint about Visa would be if you were a blockchain person, you said it is not decentralized.
Yeah.
Okay.
Yeah. Cool. So I guess that is mostly what I have. I'm happy to like go more into depth of anything. But yeah. Yeah. So if anyone has questions, go ahead.
Up at the longest chain.
Yeah.
I've realized it's not people, but how many participants are adding to that chain?
How many participants are added? Oh, okay. So it's like, so do you mean like how many kind of transactions, like in every block, or
how can I explain?
or like how many people are actually like participating?
But they're not people. So I mean,
yeah, no, sure, but yeah.
How many are trying to get into that longest, are adding to that chain?
Yeah, so I think so the chain itself is really just keeping track of the transactions that those people are submitting. So it doesn't necessarily care who submitted those transactions at all.
Right.
So it's possible that like all of the transactions in one block came from one guy, and he just had a lot that wanted to get done. It's not very realistic, maybe, but maybe more realistic is that there's like 200 different people who each had a transaction or two, and they all submitted their transactions. Some miner like took that in. It's like, okay, I'll try to mine that for you, and then so those transactions were added. They were added to the block. The miner mined that block onto the longest chain, and then the transactions from those 200 people got added. So yeah, realistically, I think I can look up the exact numbers of like how many transactions, but yeah, probably like between like 100 and 1,000 transactions potentially from different people for every block. Yeah.
Okay, that's much less than I thought. That's cool.
Yeah. It's actually pretty small. Yeah. And like for Bitcoin, for some context, like this is like every 10 minutes a block gets added. So it's pretty slow. In Ethereum, it's every 13 seconds, but the block is much smaller. So so there's different thoughts about how you should do this and everything. But yeah.
But it's got more data potentially. I mean, going back to that Ethereum, so it's got fewer transactions per block, but each transaction might have a whole lot more data that they have to contend with, which is probably why it's got a smaller block size.
I think the bigger reason why it has a smaller block size is that is because we're trying to iterate very quickly.
Yeah.
Right. We're like the difficulty is much lower, so to mine a single block, it doesn't take quite as much. Yeah.
Okay. Will all cryptocurrencies switch over to be proof of stake versus proof of work?
Not necessarily.
Not necessarily.
Not necessarily all will switch over. Yeah.
Or some of them
Like
switching over?
some, yes. So that's a good question. So one key crypto or blockchain that's trying to switch over to proof of stake from proof of work is Ethereum. So it's been proof of work for its like entire life, and now it's finally realizing it's like, yep, proof of stake is kind of a better option. So we're gonna switch over to there.
It's just trying to be green, really, isn't it? Is that
That's part of it.
motivator?
That's definitely part of it. Yeah. Yeah. Yeah.
You want to field other questions?
Yeah. No. Anyone has questions, welcome to it. Yeah. Or just comments or anything.
Or if you didn't cover something that they were interested in.
Yeah. No, if you're anything you want to talk about. Yeah.
The proof of work. You said 2 to the 64th is what most people keep it down to that. Are there people that only work higher than that?
So the 2 to the 64, that's just like an example of what the difficulty might be.
Right. So are there people who work more difficult? They would rather work 2 to.
Yeah, I see. So basically, there's no real incentive to force yourself to work at a more difficult level, because so long as you're like, you get a number below that threshold, it's good. So it's like, it's binary. Either it's good or it's not good. And depending on that, you can, you can either say like, yep, I'm going to add this block now since I found a good one, or nope, it's no good, so I'm going to keep mining. Yeah.
Okay, thank you.
Yeah. Or you have questions about like how some of these are practical? How that might, yeah, like that could definitely be. I could see that being a reasonable question about like, so what BFT type versus longest chain, like what's the point? Or like proof of work versus proof of stake, whatever. Yeah.
Do we have practical examples of both, two different industries using proof of, or the BFT versus longest chain? Most of the cryptos are longest chain, but who's using BFT?
So like definitely like a banking industry or like finance especially are really who are the main people who are using BFT, I think, because they want to really guarantee their transactions agree with each other, basically. Yeah.
It's still financial in both cases then.
It could be, yeah. No, but so like
historical banking was like a Chase bank, or what's it, Jamie Dimon's thing is Chase, right? It's Chase, JP Morgan. They're notorious for not supporting regular cryptocurrencies. But is there a relationship to longest chain in part of their reasoning? Like they don't trust a longest chain kind of solution, they only trust BFT, or is that, am I way off the scale of your stupid question?
Yeah, I mean, I could see like some kind of banking company like not liking longest chain because specifically longest chain because of the potential validity issues, and like you have to maybe wait a really long time for it to be really have some high guarantees. But at the same time, because the BFT type blockchains are usually much smaller, this means that they can also be kind of overwhelmed with attackers more. And that could also be kind of detrimental. So part of it has to do with there just not being very many really big BFT type cryptocurrencies. Yeah.
Is there an example, like if I wanted to buy some, trade $5 to get whatever the current exchange rate is for Ethereum, that's a transaction. And it's possible that that transaction never makes it onto the blockchain because for the same reasons you were describing before, it's a longest chain thing. So is that the sort of thing?
No,
that would be
definitely.
like,
So like,
sorry, it's not
some of your you might get a transaction that gets onto a block, but not the longest chain block.
and therefore never gets reported.
So at that point, you would probably like whatever client you're using would hopefully retry the transaction or like make sure that you still want to do it and then retry it.
Would they get the same exchange rate, or would it maybe be in a different exchange rate at that point?
That's all off chain. So depending on whatever client you're using or whatever, because really what you're doing there is like you're going kind of like half on chain, half off chain, right? Because it's like almost you have to validate like maybe the US dollar transaction external to the chain. But then once it's actually on the chain, then you can like have some guarantee to like send the Bitcoin your way.
Okay.
But yeah, I think like when you're like buying with the fiat currency like that, it can be a little a little kind of hacky, I guess. Yeah.
All right. Okay. Any other questions?
Yeah.
This is very informative. Thank you.
Good. I hope it wasn't too technical.
No, but you broke it down well for me.
Okay.
It's technical, but you made it easier for me.
Okay, good.
Well, thanks, Marcus.
Well, yeah.
That was really fun.
Sure.
I really put him on the spot because when he came home from lunch, I said, "Hey, do you mind doing a webinar today?" That was a blast.
Yeah.
Good.
Yeah, thank you.
Yeah.
All right, more later then.
Yeah.
Yeah.
Thanks, everybody. I'll save the recording if anybody wants to go over it again.
All right.
Okay.
Sounds good.
All right.
Bye-bye.
Thank you, Marcus. Bye.
Thank you.
Excellent. This is I've shown this sheet to you before, right?